let me record this session real quick and make sure these messages are not blocking my view. All right, so today we will move on to dive deeper into C. I'm not going to have an in-class exercise toward the end of this class, but I'll again do the sample code, basically coding exercise. I have a few examples that I plan that I'll just basically live code so that you can see all my potential bugs that happen to my code, and also potentially ways to detect it using one of the tools you learned in this class, in this lecture today called GDB. So let's begin. And the first thing, let's resume from where we left off, right? So on Tuesday, we were talking about, hey, how to use loop, how to use if-else statement. Today, well, actually at the end of the live coding on Tuesday, we implement Fibonacci without using array, right? We use what computer scientists would call a technique called dynamic programming. What is dynamic programming? Basically, we memorize the results of the last thing we compute so that we can accelerate, make things faster for the next piece of results that we will generate, right? Is this similar to like you did work already, right? Don't redo that work again. So that's the core of dynamic programming. And one of the key things in essentially dynamic programming, right, is array. What is an array? So I remember at least either one student, like a few students here in this section or in the next section, basically asking if I can kind of reiterate what is dynamic programming, and the answer is yes, I will definitely do that before I go into how to use an array in C. Otherwise, it's going to confuse a heck out of you, especially if you forgot what is an array. So for those of you who use an array before and remember what is an array, can you kind of summarize what is your understanding of an array? It's a storage, right, of data. That's like actually almost perfect definition of an array. Let's say you have a lot of data, a lot of integer, 1, 2, 3, 4, 5, 6, 7, 10, 20, 29, 31, 33, or random number. And you want to store them so that your program can refer to them later, right? You can use an array for that. So what is an array? Array is essentially a collection of data. Then it should have the same type, right? If it's an integer, everything in your array should be an integer. If it's a character, everything in your array should be a character. Guess what? The string, as you know it, in C, in C, and actually in many languages, what is a string? It's a bunch of character, right? Put together, and it creates a word and a string and a sentence, a paragraph, right? So in C, we use array to store string. It's an array of character, right? So one unique thing of array is if you think about your oops, sorry, I need my pen, not my laser pointer. So if you say buy a DRAM, right? So this is your DRAM. Because I'm from architecture side, I always refer to memory as DRAM. It's actually the main memory, right? This is, as I said, where everything store your data, right? The program when you run is somewhere here, program, right? And when you initialize an array, you say, hey, I want this collection of items of integers that I want you to use later, right? This will be allocated in a different portion of your DRAM. This is where your data is stored. we'll go into a little bit deeper into the organization, because there's a part where can keep growing and shrinking, and there's another part that's static. It should be kind of like defined as 10 bytes. It should be 10 bytes, 20 bytes, 20 bytes. It won't grow, it won't shrink. So an array will be stored here, right? Inside the portion where you store the data. So let's call this array of integer. Let's say I want to create an array of integer. I can call int, right? Array, I just name it ARR, and that should be 5 of them, right? I want to initialize five pieces of integer that I can store later, right? It will look like this. So each one of this is an int, an int, 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 and int. This is ARR of 0. This one. This is ARR of 1. This would be ARR of what? There are 5 of them. Start with 0. What's the 5th element? Is it ARR of 4 or 5? It should be 4, right? It should be ARR 4. If you say 5, go get coffee. The reason why I said they are contiguous in memory is this. Let's say you lay out the addresses from address 0 to address whatever in your DRAM. These ARR will be allocated here, where this first piece is ARR of 0. The next one will be ARR of 1. The last one will be ARR of 4. Basically, it will be linked together in one big block, right? So that's an array. And this is actually the beauty of C, because you can actually go and point to that location using an address, which is unique. In most programming language, you just refer to this as, say, ARR of 1, right? To get the first element. I mean, the second element, ARR 1 is the second element. The first element is ARR of 0. In C, you can just throw in number. If you know the address, let's say this address is at 100, you can say, I want to get the element at 100, and I know it's an integer. You can just say print the location at 100, integer type. It will actually print ARR of 1. So in C, you can use this bracket, right, to specify an array of certain data type. For example, you can say int I10. This means I will create an array of size 10, right? It can store integer. A character, I can say char A20. It will create an array of character of size 20. I can say, hey, this character A equal hello, right? It basically means that if I print A, it should print hello. So my question is, when I print this character, it becomes a string, right? It's just an array of character. How can I tell that it's the end of the string? So one way that C represent a string, right? Yes. So there's a question whether A and I are the variable name. Yes, they are variable name. You can refer to A and I later, right? And to have a string, basically this is what A would look like, right? So actually A of 0, right? A of 1, A of 2, and I'm glad I just typed in hello because it's not too long. A of 4. So you have H in the first letter, E, L, L, O. I can tell that that's the end of my string by just insert the value 0 here. It's a noun character. Say, hey, if I see 0, that's the end of my word. Whatever goes in here, I don't care. I don't care. And actually, if you know, so we're not going to cover it in this class, but if you look up the technique called buffer overflow, you can use this string to kind of like, you don't stop at 0, somehow you overwrite that. And afterward, you keep writing. You keep writing so that if you look at this diagram where you have program and data, right? The data for your string kind of like go here and overwrite your program. That's how you can actually hack someone's computer. That's like a old, like classic way to do this. These days, Windows has a lot of protection against that. So it's not going to be effective now, right? But this technique is called buffer overflow. So if you want to look it up, feel free to. If you want to kind of dig deeper into this, ping me. I wouldn't mind sharing. As in, I'm not sharing how to hack things. That's not my job, and I'm not a good hacker at all, right? So, but I tell you how it works. I can tell you what I can do. Basically, replace a function in your program with your own function. Essentially, you're trying to overwrite the program. I don't like how the virus works, right? Embedded itself and overwrite the program so it knows what you designed it to do rather than what the program originally is designed to do. So you talk about the array. Array is a collection of the same items, right? Of the same items. And now you're like, hey, what about, let's say I want to store a map, or like I want to store a pair of data where I want to pair a character and an int together, right? So you can use this thing called struct for that. It combines multiple elements: integer, string, floating point, double, 2 string and 1 double, 5 strings, 1 more character and 1 integer, right? This is called a struct, and you can use it to essentially create this block of data, right? You can call a struct. This is the name of the struct. Some name, you put a name there, whatever you wanted to name it, make it creative, make it not creative, up to you. There was a joke about Ajahn Kanat back when I was a CMU student that his code is just A, B, C, D, E, F, G, and reading his code is a nightmare. I'm sure he's changed. That was like when we are all young, right? And we just want to make sure we get the homework done and submit it on time. But yeah, put in name. And I'm not even sure if that's true or not. I never seen this code. So in there, you just declare whatever you want to declare that would be there inside the struct, right? So these basically create a structure called some name with an integer and a float inside it. And to access, let's say you want to access A or access B, you can say some name.a. This will give you the int element, or some name.b will give you the floating point element, right? Hopefully this is self-explanatory. It's not hard, right? It's just syntax. You just need to type the correct letters and it will give you what you want. Make sure you have the semicolon at the end. To basically, semicolon, it should be at the end of the statement for every single statement you put in C. It tells you that command is that's the end of the command, right? Over here, the command is, I'm going to create a struct called some name with an int and a float inside it. You can actually then, if you combine array and struct, right? You can then create an array of structs, right? For example, something like this. You can say struct some name and then put in the bracket at the end. Now, ARR underscore name will have 100 items. You can say, okay, the first item, I want to get the first element, right? The int element of the first struct in your array. So I'm going to show you, not show you, but give you one example why you might want to do this. What is in 1 pixel on your screen? What are the values that you have to store for each of the pixel? There's a color, right? There is also the intensity, or sometimes we call it the alpha. Yes, the RGB, right? So the RGB value essentially stands for red, green, and blue, right? If you're not failing art like I do, you will know that you can mix these three colors and get every color that the eye can see, or at least that's like close to every color that the eye can see. I'm not sure the theory behind it, whether it actually cover everything or not. But it cover a wide spectrum of colors, right? So in a pixel, it will have the value, right, of the red, the value of the green, and the value of the blue color, right? And when you combine all of them, you get one pixel's color. It can be orange, white, black. As long as your monitor is not broken at that particular dot, you will see a color, right? So, how big is your monitor? As in not big in the size, but like what's the aspect ratio? What's it called? The 2080 multiplied by 1920, right? So your monitor, the HD monitor is 4K, right? So it's something like that, right? So there are, yeah, resolution. Thank you so much. Sorry, guys. Uh, so that's a resolution. It means that it contains that many pixels, right? So you can create an array called, I guess, monitor color, right? With this size 190 1080, right? Inside here is a struct, right? That has actually the value between each of these color is only 0 to 255, right? So I can use a character for that because it's perfectly 1 byte. And this thing will complain because I don't have semicolon at the end and the bracket semicolon again. And now I have a struct array 2D. One dimension is 1920, the other dimension is 1080. That can contain 3 colors, right? And then you can say monitor color of, I guess, 10, I don't know, some random number, 15 dot blue equal, I guess, 255 because you want it to be super blue, right? So you can do this. In fact, many graphic programs make a struct that looks kind of like this so that they can manage the thing that they want to show on your monitor, right? So you can see how array of struct can be useful. Defining a new data type, basically you can define, now that you create a struct, right? You can say type def using the command, right? Now that we just create the pixel value, right? So you can say type def. What was a struct name? Let's go back. It's called monitor color, right? So I can say type def struct monitor color. All right, how should we name this? Put in a name. Give me a name. Give me a name. Any name. You can name the variable any name you want. So I guess I ran out of idea. So I just said temp. That's a really stupid name. Okay, that's okay. All right. Full hacking. Okay. I will just combine the two. Yeah, you can name it that way. And you can say full underscore hacking 190 by 1080. This will do the same thing. I'm gonna create a struct with the type monitor color. It's a 2D array with 1920 elements by 1080 elements, right? So that's it. Any questions about how to use array or struct? All right. So if there's no question so far, the next thing we'll cover is what we call pointer. So if you are going, if you feel sleepy, wake up. This is where it will confuse This is the most painful part about the C programming for this class. That's how I should put it. And it's not hard. It's not hard. You just need to be like a little bit aware of what you're coding or what you're writing on your code. So think about it. How does C actually stores its data, right? When I say I allocate an array, it's allocated somewhere in your memory, right? So every piece of data or variables that a program uses is stored somewhere in DRAM or your main memory, right? Every piece of data has its own address. Think of it this way. Let's say when you want to use a variable, when you create a new variable, you need to like buy a house for that variable, right? Somewhere you can store the data, and let's just say it's a house. You need to make sure that if you want to refer to that variable, you need to be able to go and look for them, right? Just like us human, right? I'm here in my home right now, right? To come and see me or to get whatever I store, right? My value, you need to have my address, right? You need to have my address. Every location of your DRAM has a unique address, ranging from, let's say it's 4 gigabytes, ranging from 0 to 4 gigabytes. 4 gigabyte, what's the number? 4 multiplied by 1024 multiplied by 1024 multiplied by 1024. So that's the last address. I guess -1 because it started with 0. But every single location in your DRAM basically have its own address that you can go to. Why? Because you store the data there. If you don't have the address, computer, so remember this, the computer we're using is super stupid. Unless we tell them exactly what to do, they can't do anything, right? Robots are not evil unless we program them to be evil. Unless you tell the computer to do certain things, it's not going to do anything. So if you want to store some data, to go back and get that data, you need to tell them, hey, go to that address to get my data. All right, everyone with me? So
is the address also a data?
it is? Well, it is a value. You think about it this way. Data, okay, let me kind of make a distinction between data and address. Data is where you hold the value for something you're trying to get, right? Address is the location of that data. Address is a value. Your data is also a value. Now, from the mathematical sense, everything has a value. The address has its own value. The data has its own value. Does it kind of answer your question, or is it even more confusing now?
So
No, please follow up question, please, to make sure we are on the same page.
this is about DRAM, right?
Yes.
And so does address take space in the DRAM also?
Oh, okay. No, and actually we will learn in the third module on what's the organization of the dealing with your data and the main memory. But think about it this way. Instead of having the address like human do, right? So I can say I'm in thisซอยบางกรวยไซน้อย 44 แขวงบางกลางเขตI meanตำบลบางกลางอำเภอเมืองนนทบุรี, right? And whatever my mailing postal code is, right? Computer make things a lot more simpler. My address, it can be 10. Your address 11, the other student address 12. Like, for example, Saran, your address is 13. Justin, your address is 14. Another Justin, I think there's another Justin here. 15. I can say go to address 15. It's a value. It's just like one value, right? So you can use that value to go to where your address is. It doesn't take any space because you know exactly where 15 is in your DRAM. That's what the hardware gives you. When you buy DRAM, when you put in the number 15 at the address bus. So I'm gonna go off topic here and into architecture. You buy DRAM. Before you actually access DRAM, there's this thing called memory controller. Memory controller is like a chip. It's a chip that's programmed just to control DRAM. How do you control it? There's a bus. A bus, think of a bus as like our bus. It transport things, right? So there's a bus to transport the address. You can say, hey, I want that address. When you give the DRAM an address, DRAM will spit out value. Basically, that's it. Give them address, I got value. This address is going to be 0, 1, 2, 3, 4, 5, whatever we want to use, right? Does it take space in DRAM? No, it just say, hey, it is kind of like my address that doesn't actually take a space in my house, right? It's just a placeholder that if you give me this address, I will show up.
Then where what was it? The order that to bring that address out.
Mm-hmm.
Where does it hold that?
Oh, okay. So I'm gonna put in abstraction because in reality it doesn't order like this. But think about it this way. Let's slice up DRAM into each byte. Each box here, I said it's just each byte in DRAM. There'll be a beginning and there'll be the end. I'll start with the zeroth byte, first byte, second byte, third byte, fourth byte, fifth byte, sixth byte. Let's say your integer, and let's assume it's 4 bytes, right? Let's say your integer is in this range. Integer is 4 bytes, right? So it's going to cover this range. And let's say the value of this is 10. This is the value. This value 10 will have the address of 4. It will just say, if I give the address 4, you should read out of this byte that represent the value 10. So the 4 here doesn't really take up space. It's just a location inside DRAM that's already been divided into different blocks, right? It's the starting at the fourth block, and we're gonna grab that first byte, second byte, third byte, and fourth byte, combine everything together. Magically, you now got 10. So does that clear up your confusion, or is it less, or is it now even more confusing? I hope it helps.
So the beginning and the end also counts as bytes?
In modern architecture, yes. You give them an address, it can be 0. 0 address will refer to this block. If I give an address 20, it will be somewhere here, right?
Then
yeah.
So then where does the memory controller get the order from?
You mean where does
command?
how does it know the location, right?
Yeah, how does it know?
So there'll be like a bunch of circuits that take in the address and it know exactly get the electrons in that capacitor. There's a lot of circuits behind it that I want to shield you from those circuitry. Where's the memory controller? That's an awesome question. Right now it's on the CPU. Is that a good decision? I'm not sure, especially because I was in a lab when I was a CMU. My lab is one of the most active in doing research on memory. There was a lot of argument about why don't we put that in DRAM? And to be honest, it's kind of like a tug of war between Intel and DRAM manufacturer on who would own this piece of thing. Right now, it's on the CPU side. Not really making things less confusing for sure. I just want to give you additional information that is not related to this class at all. Sorry. But that's a great question. This is a great question because you know what? You see the pin, right, that connects your DRAM between your DRAM and the motherboard. When you plug your DRAM onto your desktop, You see that's like this DRAM slot, right? That you need to plug it in.
Yeah.
It just happened to be connecting this thing, right? This thing. It's like that pin is like in between this. So that pin is actually one tiny thing there. It's actually one wire, right? 1 bit. You can transfer 1 bit through each like little thing there. So that means it limit your bandwidth, right? It really limit your bandwidth because how wide that thing is, the more data you can send through. So there's a lot of arguments saying, hey, why don't you put that memory controller after that pin? So we have more bandwidth because everything is on the DRAM side. It's on that package. So that's why I said it's a great question because there's a lot of things going on in the memory controller that would need to be used to control DRAM. So somehow it might make more sense to put it there. If you read Hacker News, actually the Linus, the guy behind Linux, right, were yelling, but he's known to be like he's not like he's pretty straightforward and he used a lot of swear word. That's how I should put it. I use a lot too, but I'm like not that level, right? So he was like yelling at Intel, like, is Intel fault for this problem? I'm like, well, yeah, I kind of like from my angle, right? A lot of things that he complained about as an architect, yep, I agree. From the system side, right? If you look at it, like, hey, some of these things somehow it doesn't make all the sense. Let's come back to your question before I confuse you even more. So is it a little bit more clear now that the address is just a number? That is an agree upon number. It's kind of like when the government like put us in every address here, right? It's agree upon that if I use this address, it will be right here where I am, right? This house. If you change the house number from 9132, now you know my address. From that number to 93, then it's the next house, right? Does that thing take up space? No, it just agree upon number between the controller, the CPU, and DRAM.
Yeah.
Something that might confuse you more afterward. Don't think about it now, but you can use an address to store an address. We'll leave it at that. Basically, this is called indirection. I'm going to go into more detail after we are clear on how to store the data.
Is it
So,
something like when we write a code in Python and what was it? Assign a value of another, what was it called? Another variables.
yeah, it's the same thing. It's the same techniques, right? You use your array or whatever that variable is not storing the data, it's storing the location of the different variable. It's the same technique. So now your address can store actual data or another address, right? So let me erase the thing because there's a lot more text on this slide. So in C, all variables has its own address. The array is a range of address, as you can imagine, right? And hopefully you don't access things outside of this range because that's illegal access. It's like, let's say I own this plot of land, right? And I know I own it. I can walk around. No one will kick me out. But if I walk around and then somehow accidentally walk outside, I'm in someone else's land, that landlord can literally kick me out, right? That's the concept here. You own a range of address, don't walk outside and read someone else's address. In C, you can create the data type that store the address. So we are getting tricky now. As I said, address is a value, so I can store that value. This is called a pointer. A pointer is just pointing to something, right? Let's say this is your DRAM. And you want to store the value 10 here. A pointer will store a value of this address. It will store the address of this variable, right? So let's visualize this a little bit. Now that I have this my own slide, blank canvas that can draw things. So let me actually draw this thing. As I said, we have DRAM. So it's going to be something that looks like the other slide that I draw earlier, right? I have DRAM. And as I said, everything begins with a 0, and let's say it ends with n, right? Zero, 1, 2, 3, 4, 5, 6, 7. Now it's a really tiny DRAM, only 8 bytes. I want to store, and let's assume every number can fit into one box, just so that everything fit here, right? I want to store 5 here. That's a value, right? That's a value. What? Oops. And let's say I call this a variable A, right? This is a variable name. A, value of this is 5. What? Oh, I cannot draw. What? Somehow I cannot draw. It refused. And not allowed. What is the address of A? What's the address of A?
It's 3.
3, yes. 3, because it's right here, right? 3 is this one. So I can say, let's say this store the address. Let's say this variable A is store the address. And let's say this thing is 7, 6, 7, 8, 9. The value, everything in the box is a value, right? So what is the value that A points to? In other words, the variable A, right? The variable A. In other words, treat this as an address. What value I get? If I say 5 is an address, A is an address, A is 5, what is the value at location 5, at address 5? You look at this, right? Hey, I have 5 here, so that is 7. Yep, perfect. So you get 7. Clear? So you can store an actual data. You can store an address. An address can basically is a number that is an address. So you can use that number to get to the next location, right? Okay. So there's a difference between data and address. As I said, let's say int a equals 10. That's a is a variable, right? It stores the data value of 10. Ampersand, the what we saw in the scanf from last lecture, right? Ampersand mean I will treat the value of A, I'll treat whatever value, which is right now 10, I'll treat that as an address. I'll treat that as an address. Ampersand A becomes the address where 10 points at, where 10 points at. And technically, this is a virtual address. We'll learn about this in the third modules on what do I mean by the virtual address. This is a big important because if we go into the cloud system or even right now in Linux where you have a lot of application, there's a benefit of using virtual address. So it's not the real location of this thing in DRAM, but it's good enough. We can refer to that address. We'll talk a little bit about this in module 3. So sorry, it used to have 4 modules. I combined 2 and 3 into one module. So everything in module 2 is 1 year ago. That's modules 2 and 3. Module 4 back 1 year ago is module 3 right now, which is how data is being organized. Here is some example. As I said earlier, I'm gonna draw the same exact example, right? 0, 1, 2, 3, 4. Oh, actually, let me just use a different number. This is address, and this is data, right? And this is address 0, address 1, address 2, address 3, address 4, address 5, address 6, address 7. And the data, I'm going to use different colors to minimize confusion. And I'll start with 15. 15, 16, 17. Oh, actually, I should not start with 15. Let me just do the reverse of this. So we start from 0 to 7. Over here will be 7, 6, 5, 4, 3, 2, 1, 0. The data I put in is the reverse of the address so that we have a proper example here. I say int a equals 10. Oh, no, not 10. Let's say a is 5 because 10 is way beyond this scope here. Let's say a is 5, right? What is ampersand a? What do I get? Treat a as an address. What's ampersand a? 2, yes. So the location, basically this is the location of a. This is address 2, right? Address 2. Another thing I can do is treat a as an actual address. So I can say store a. Store a means I'm going to look at this value, 5, use that as an address. So what's the address? What's the value at address 5? What's the value at address 5? So treat a as an address. So no. It's actually, no, that confuses. That might be a little bit confusing. So sorry. Basically, it's not 2. Address of a, right? Ampersand a is this is the address of a, which obviously is 2, right? Because 5 is located here, right? Store a means I'm gonna treat this as an address. So I'm gonna treat 5 literally as this is the address. So I'm gonna look here. What's the value of this? 2. Oh yeah, still 2. Sorry. I was stupid. I was like, okay. So star A, treat value as an address and look at this location. It just happened to be the value too. Sorry. So I can say now, let's say I do star A equals 10. Like I just write a statement star A equals 10. This is what will happen. I will look at this. I say, okay, I'm going to replace the value with the value 10. I'm just going to replace this number 2. I will overwrite this by the value 10. Right? Oh, that's a great question. Is the order of the address dependent on the order of the program that declare the variable? The way the operating system, so this has to go to the operating system topic quite a lot, actually. There's a program, there's a piece of function that say whenever I see int something or allocate some address, it will call that function, say, give me an empty address, an address where no one owns it yet, so that I can use it to store my value. The OS maintain that mapping between, oh, this program, the variable is this of this program goes there. There's a policy that you can design when you hack the kernel that you can do whatever you want it to do. So it doesn't depend on the order of the program that declare the variable, but it might. So I'm not sure if that actually totally answer your question in a non-confusing way, But the answer is it depends, and it depends on how the OS implement this mapping, right? It depends because this mapping can actually impact performance quite a bit. Yeah, but that's a great question. So you can use a pointer like this. So you can install this create, right? This basically create a pointer called a, and the address at a will have the value of 10. A is a pointer that store an address. That location will store the data that has the value 10. Store A will give you 10. Store A gives you 10 because A is an address, location, store 10. You can use ampersand on a variable to get an address. You can use store on a pointer to get its value. You can make pointer points to other variables too. As I said, you can keep pointing, right? You can keep pointing. So you can also do an operation on a pointer. You can do a plus plus, go to the next elements of a, next element, right? So let's say this is address 9, address 10, address 11, address 12, address 13, address 14, and let's say 10 is right here. This is where a is, right? So a plus plus will point to the next element. And let's say this value is 13. A plus plus star a plus plus will give you 13. You go to the next element, dereference, you get 13. Using store and pointer is called dereferencing. Get the value that the address point to. Ampersand is called referencing. Get the address of that. And C, you can use ampersand on the address. It will give you some number. Does that number mean anything? No. It will give you some number because it will try to dereference that pointer, and I mean it try to get the reference to that pointer, but it doesn't mean much because that's the lowest level you can go. But you can dereference to get the pointer to point to the value. That value can store an address, so you can dereference it again to get the next value. What about that? Sorry. What about an array? So when you declare an array, you are creating this pointer that cover a range, right? So an array of int with 4 elements is the same as the pointer that can move up and down this range. So every entry will take n bits. Let's say int is 4 bytes, right? Let's say int is 4 bytes. If int is 4 bytes. Let's say int A4 means that I'm going to create an array of 4 items, right? This is A. This will be A plus 4. This is A plus 1, A plus 2, A plus 3. The first item of A, the second item of A, the third item of A, and the fourth item of A. This is from the actual, so the actual address. Let's say A has a value of 10. Let's say A is a value of 10, it's at byte 10, it's at byte number 10. A plus 1 will be at byte number what? 10, 11, 12, 13 will be a part of A, right? So A plus 1 will start at 14. A plus 2 will start at 18, right? A plus 3 will start at 22. It will be that data size, and when you increment, right, A plus 1, it will actually get bumped by the size. Because there's no point going in the middle unless you really know what you're doing. So A bracket 5, which is accessing the 6 elements, is the same as A plus 5 and then the reference, right? Assuming that you have the memory, assuming you own the memory. Ampersand in bracket, in the bracket A5 is similar to A plus 5, the value that because you're trying to get the address, right? You're trying to get the address of A5. And before we move on, when you're playing with pointer, there's this thing called null pointer, because pointer by definition point to something. It's an address, right? It's an address to something. But when you initialize a pointer, it doesn't point to anything yet until you assign an address to the pointer. So a pointer can take a value. It doesn't have to point to anything. This is the null pointer. Why do you need this? Why do you need the null pointer? Let's say you create an integer, the pointer for integer, and you did not initialize that. You want to make sure you do not accidentally use the value because it points to some meaningless location. You haven't actually assigned any value to that yet, right? So to prevent bugs, everything you should be assigned to a null pointer to make sure it doesn't do weird thing. In C, you can then assign this null pointer to a value later, right? You can also assign a pointer if you don't want them to point to anything, say equals null, NULL. You force the system to know that, hey, this pointer is not pointing to anything yet. Accessing the value will generate an error to make sure you don't do something crazy because it haven't been initialized. Data type has its own size, right? You can use, as we discussed on Tuesday, you can use the keyword size of to check the data size. So you can check data size of an actual data type, right? Like this. So this data type itself. This is a variable. So you do a size of variable, it will actually print how many bytes does that variable consume. Store is called dereferencing. You have an address, you want to dereference the address. Ampersand is called referencing. You have a value, you want to get the address for the data. So what does this do? Store ampersand A. It equals to A, right? You try to dereference and then reference it back. So A. Oh my bad. You try to first do the call reference. You try to reference because you have the ampersand and then dereference. So it got back to the value A. Things to be careful when you use a pointer. Make sure you first declare them. Right? This is normal, like computing 101. You want to use anything, declare the name. Then make sure it points to a valid location. Otherwise, it's basically something weird, right? It's not a valid location. So before you use it, make sure it points to a valid location. Otherwise, using that pointer, it's become illegal. Think of it as you trespassing on someone else's home, right? That's illegal. You should not do that. So make sure it's your own, already allocated, and you own it. You can use the pointer to point to the file as well, right? When you want to open a file, you can use pointer for that. This is done through a keyword called file. File is a data type. It's a special data type that points to a file. You can say file store, file pointer name. The name of the pointer. It can be something like this. Store A. A more common would be, I can say the name is FP, right? FP. Can then say FP equal F open. F open is a function that open the file. It just open the file. You can put the path here, so it can be this /home/rashada /test.text in quote because you want a string there, right? What are the mode? Mode you can have read or write, essentially self-explanatory. You want to either read from a file or write to a file, right? After you're done, close it. Don't open a file and not close it. It's going to end up being odd from the file system point of view. So you open and then you close. And let me tell you, I did make this mistake many times. I think the modern version of GCC will close it for you. Along with the modern version of operating system, they'll actually check and close it for you, but make sure you close it. That's the safest thing you can do. You can check this on how to use it. Opening screen. Right? If there's an error, fopen will return null. For example, let's say this file doesn't exist. Let's say the test.txt in my home folder doesn't exist, it will return null. So I know that, hey, something is wrong with the path, it cannot be read, it cannot be written over. You can read from a file using, instead of scanf, scanf, just add the letter F. Put in the file pointer. For example, earlier our file pointer name is fp, so we can do fp. Read, and you put in what you want to read, followed by what is a variable that you want to store the content as. Basically, this is reading one integer into A. The same concept apply for the function getC. getC is get one character. GetS is get a string, right? You can check this link. It will tell you what are the other example. You can write to a file. Instead of printf, this is writing to your monitor. You do fprintf, writing to a file. This would write one integer A. And to tell that you've been reading through the whole file, there's a special value at the end of the file. It's called the end of file, literally the end of file, EOF. The end of the file is denoted as the end of file. You can use this function called FEOF and put in the file pointer. For example, we declare the name of our file pointer FP, right? So you can do FEOF, FP, to check if that's the end of our file, right? Stream.io generally is used to access inputs or outputs such as file, keyboard input, printer, terminal, right? So you can use it to do things in order to interface with the input and output. Input and output are file, keyboard, network drive, network location, even things like network port. This is done through Stream.io. All right. So let's take a quick break. In the meantime, feel free to ask any questions. It's a lot of content for now. So let's do a break in the middle before we move on to talking about memory allocation. Yes?
So in C, we cannot keep appending arrays like a list.
That's a great question. And the answer is you can to some extent, but you need to create a new array, then copy the content over.
Yeah, because if you reach a limit, you cannot add it more, right?
If you reach a limit, you can, as I said, you need to kind of double the size by allocating a new array, copy the content over. In the real program, actually, if you want to do so in Java, or actually in Python, you can do that, right?
Yeah.
Behind the scene, the same thing happens.
Oh.
It actually, yes. In Python, let's say you want to append in an array, right? Everything boils down to the basic. You already allocate the same size of an array. So what Python would do, create a new array that's bigger, right? And then copy all the content over. Yeah.
Oh, so it does those things behind
Yes.
your back?
Yes, it does those things behind your back. To be honest, because we are learning C, right? Everything in C is it at the end of the day turns into assembly.
Mm-hmm.
Once you compile your code, a lot of things, a lot of functions you declare, there's also things that are optimized that are doing behind your back to make it faster. For example, let's just come up with some example. This is unrelated to this allocation cost and pointer, but let's say I want to do let's say I have a value of a which is 10. If I want to do a multiplied by 4, which is 40, right? I want to get 40. Multiply by 4. Multiply operation takes a lot of time compared to an add, compared to a shift. So I can do a shift left by 2. This is exactly the same as 40. You learn this in a bit, but basically the compiler can detect this, change that line to a left shift by 2. You get 40. It's about, in a modern shift, this is about 10 times faster.
Oh.
Yeah. Or a little bit less, maybe 5 times faster. Multiplication these days is not that bad. But this is one example of like compiler doing things behind your back to make it faster. Python do those things behind your back to make it more programmable. You don't have to worry about the size of your array. You don't have to do things manually. In C, you need to do that on your own.
Is that why you said that C is faster than Python?
In a lot of cases, yes. A lot of things that Python do behind your back is to support weird things you want them to do.
Oh.
And it's like, think about it kind of this way. It's like all the libraries that are available for Python are kind of pre-coded and actually they optimize it so it's not that slow. Like it's not that slow. But they optimize it for what you want them to do. In C, because you program everything on your own, you kind of like just hand tune everything. It gives you ability to hand tune things. Is there also that's a great question. That's a question on the chat. Is there a built-in array list similar to Java? There's no built-in, but you can create a list in C using pointers. We will learn that next week, actually. So you can then create a list of array. All right. So let's take a quick break. Here. I can't. Okay, they're all sleeping. So let's do a quick break and meet again in 5 minutes, 1:18.
Yeah,
In the meantime, ask question. Yeah.
one last thing.
Yeah.
I kind of forgot to do the things about GCC.
What do you mean the thing about GCC? What can you define
So
thing?
you said we need to. Do I have to download the GCC for Windows?
Oh, you mean in class exercise, right?
Yeah.
Yeah, don't worry. We have the server now, so you're good.
Oh, I thought that I need the GCC also.
You need the GCC somewhere. So if you want to program on the server, just feel free to program on the server. As a question on the chat, is it recommended to use Visual Studio for C? Up to you. I use Vim. So I have heard great things about Visual Studio. I have heard great things about IntelliJ, but be careful with IntelliJ's memory consumption a little bit. Somehow it uses a lot of memory. But it does provide you with a really nice interface. So hopefully that kind of like, it doesn't fully address the question, but it's your preference. I have to be like honest here. And my recommendation, try it out. If you like it, use it. If you don't like it, move on and to go to the next IDE.
It's just that when I tried searching GCC for Windows, the website, the mingw.org, it doesn't respond.
Oh, so if you have a Windows machine, just use our server or install VM with Linux. I actually, again, I don't really like the option of like dual booting because it kind of like dangerous if you don't manage it carefully. So using a VM is easier to manage, especially if it's only class related. If you don't have to like deploy things and you really need to booting, I mean, just use VM. Yeah, but our server is fully capable of running C code.
And that's about the assignment part about the what
Linux.
was it called, put it from this skill to the local.
Copying things over back to the local area, local computer, right?
Yeah, do I need any
So if you should know how to do it actually. In Windows, there's a software called WinSCP that you can use. It's a Windows SCP. It's free. I used it before. I kind of used it while I was at CMU. I use it now. And that kind of worked. For Mac, you can just use SCP. Mac actually is Unix, so it does support SCP. I'm sure that might be like a MS-DOS, like command prompt version of SCP. I didn't bother look it up. Maybe I should look it up. I usually just use WinSCP because it looks like a window explorer. Once you connect, you can just drag and drop things.
Okay.
All right. Okay, so it's 1:17. So since I said 1:18, so let's wait one more minute uh and let's resume. I'm kind of like in between whether I should play with my cats or just let them sleep.
I
Because we have
thought
one
that
day.
I would have to download Git.
You thought you have to download Git.
Yeah.
So if you want to use Git on your machine, if it's Windows, there's a thing called Git Bash, which first of all, it will allow you to use command for Git on a terminal like thing, right? So it's pretty neat. I use it and I kind of like it. And also heard good things about Windows subsystem for Linux. I never personally try it because my office has a Ubuntu desktop, so I didn't bother to try that. But I've heard good things about it from many of your friends at MUIC.
What do you mean subsystem?
Oh, so if you Google, let me show it to you.
Okay.
So if you Google this, Windows subsystem for Linux, it's a software on Windows 10 that would kind of like once you set it up and install this, you get to use Linux-like command on Windows.
Oh.
Yeah. It's a Linux distribution that integrated with Windows, even though Windows is not Unix based.
So it translates the command from Linux to Windows?
Yeah, I think they kind of emulate. So I think what happened is there might be building a virtual machine inside your Windows that have Linux kernel on it.
Okay.
But this VM, the virtual machine, is likely much more like Windows friendly. So you can emulate the hardware from inside Linux faster. So I've heard that this is actually faster than using VM. All right, so now it's 1:19. So let's continue on. I hope we finish by the end of this class, but if not, I'm going to then do sample coding next Tuesday, and we'll do a big recap so that we refresh what we learned today. It's a lot of material, I understand. So hopefully you all bear with me. So what's memory allocation? This is a big, huge part of C. So when you declare a variable, right, as I said, data take up space. the program actually allocates the memory for all the variables that you define. Int I, for example, right? When you write in int I, compile the code, the compiler actually know, okay, int I means that I need to create 4 bytes for I, right? It also allocates blocks of memory for an array. Int A of 10 will create 40 bytes for A, right? It's 4 times 10, so it would actually pre-create that, right? You can then, afterward, if you want to like create a new thing, right? You can use pointer and you can manually allocate memory for pointers. So these pre-allocation will go into the area on your DRAM that's called a stack. This will go to an area called a heap. So if you look at DRAM, right, DRAM, there'll be some area for the stack that is static, it won't grow. Once you run the program, it won't grow, it will be that size, but the heap will happen depending on how you allocate or deallocate things, right? So these are for pointers that you allocate. And how do you allocate memory? As I said, static allocation is done when you use an array, right? You know exactly you need 40 bytes. When you declare int I10, you know exactly what's the size. Int A of 10, you know exactly what's the size of A. But if you do this, int B store, do we ever know by the time we run the code? Before we run the code, we don't know what's the size of B, right? The computer cannot tell. So you can then use dynamic memory allocation. This is done through calling this function called malloc. Malloc is memory allocation. That's why it's malloc. M is for memory. Alloc is allocation. I'm going to allocate 10 multiplied by size of int. What size of int? 4. So basically this whole thing gives 40 bytes to A. Basically what it means is the system will go find where is the empty 40 bytes of data in my DRAM that I can use. Where's the empty lot of data that I can use for A. Once you found it, let's say you know that address 10 to address 50, so that's 40 bytes, right? Address 10 to 50 is empty. You give this to A, so A will equal 10. A plus 1 will equal 14. A plus 10, or actually A plus 9 will equal 46. So this will be from address 10 to address 49, right? This basically means I'm going to go find a free location of my DRAM, allocate this location for pointer A, and now A will point to the beginning of that block. Think of it as the system go and find an empty LAN in your DRAM. Think of DRAM as a big giant LAN that you can use. It will go find an empty lot in that LAN, and then that lot should fit at least fit 10 integer. Give that lot to A. Then A know the address, right? So A will take this address. Here's some example. Let's say I do int store P equal malloc 20 multiplied by size of int, right? For I, okay, in I want to declare I too. For I equals 0, I is less than 20, I plus plus. Store P plus I equal I. What does this do? What does this do? What does this field support do? So this means I'm gonna create, right? 20 integer for P that basically it would look like an array. P is now an array, consists of 20 integer. What does P of 0 store here? P of 0 is store P, right? That's when I is 0, if I is 0. Then, what is P of 0? 0, right? P0 is when I is 0. P of 1 is 1, right? The third time we go through the loop, P of 2, when I is 2, that's 2. This is initializing everything to 1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, up to 19. Right? So this is how you can use memory allocation. What if you want to increase, exactly as that question we got earlier? If you want to increase the size of your array, what do you have to do? You use malloc. Create a temp pointer, allocate a bigger size, copy, deallocate the old thing. So let's say you have int or p, right? And you say, okay, p equal malloc 4 times size of int. Right now it's a array of size 4. And you say, hey, I want to make it 8. I know that I need more than 4. What do? I can say int store temp equal malloc 8 multiplied by size of int, right? So now you have p of size 4, right? And then temp of size 8. And then you do the copy, basically copy this content over from here to here, right? Copy, and then you say free p. Free p means that now that you copy everything to temp, you clear this up. Say, hey, I don't need to use this part anymore. Someone can use it. Then you say p equal temp. Now p will point to here, which is the same location as temp, right? And that's it. This is how you can expand your array. And this is actually what's going behind the scene when you use Python, like expanding an array in Python. Make a duplicate, copy everything over, make sure everything now point to the new one, and deallocate the old unused land, right? So we talk about deallocate. The deallocation cause is basically when you know that you no longer need to use this allocated area anymore. You're done. Sorry. You can then mark the region as free so that someone else can use this region later. This is called deallocation, and this can be done by calling free, put a pointer name in there. You want to make sure that you do this to avoid the big problem in like coding in C. Essentially, is called memory leak. Basically, your computer run out of memory because you never free things. You keep allocating, and you forgot to free. At some point, you use and allocate every single address in your memory to the point no one can use it anymore. All right, now that I mentioned heap and stack. Pointer can point to both heap and stack, but the stack is the part of DRAM where when you run the program when you launch the program, right? Because you know that if I say int I of 10, right? I know this is an array of size 10. These are pre-allocated for you. The computer actually allocates this for you ahead of time. This is used for normal variables or arrays, right? Any static memory allocation that the computer knows will be allocated beforehand, put on the stack. Heap is when the memory is allocated while running, when you call malloc. When you call malloc, this makes the heap grow in size. When you free, the heap would shrink in size, right? So what are the use of pointer, right? You use it for dynamic memory allocation, and you can use on things like linked list, tree. You can use it to pass data into a function or get data out of the function. You can return more than one thing. Pass in the pointer, do something with it. Don't have to return because you just update that address. I'll show that example in a bit, right? Pointer can be assigned to a function as well. We'll get to this later. It's called function pointer. More thing to consider. There's also this void data type. It means that doesn't have a data type. It means nothing. Void literally mean nothing. So a function can have void as a return type. It doesn't return. It's just basically say, hey, this function doesn't return any value. A pointer can be a void type. It just means it's an address, but doesn't have a particular specific type. You can just then manually cast the data type later. You can say void star temp. And if you want temp for integer, you can say int star temp, right? This means that I'm going to cast temp to be integer pointer so that you can use it later. This can be used for function pointer. Basically, you then cast it to be a function type, that exact function, and use it to call function. We are not going to cover it today. We will use that for next week. Again, we can cast similar to variable. We can cast pointer type. Int star in parentheses means the pointer of integer. This means pointer of float, etc., etc. Const is a declaration that this variable will not be changed. It's a constant. So const int star a means that I can have a. A can point to anything. But when we use a, it can point to many things, but this pointer will point to a data that are constant. We cannot modify the data. Int const a means that I cannot change the content that a points to, but, oh, sorry. I can change the value, but I cannot change the address of a, right? This means I make the int constant. This means I make the pointer constant. So const ties to what follow that. Const make the value here, right? Because it's next to the int. This is pointer. So it depends on what you put const next to, right? What about this? Const int star const a. Now everything is a constant, right? I cannot change the address of a. I cannot change the value of whatever a points to. You can use const on a function declaration. It just simply means that I cannot change the address of the function. Right. So how can you debug your C code? One last thing is like, okay, now that I give you a lot of syntax, right? How to use a pointer, how to use the address. A lot of time when you use it for the first time, it's going to get buggy. And when you use address, memory allocation, your compiler might not spit out meaningful warning or meaningful error. It will just throw away something called segmentation fault when you run your code. You can use this thing called GDB to use GDB to debug your program. To do that, when you compile the code, add the -g. To start using GDB, instead of running, say, fib.o that I had earlier, right? I can type in GDB fib.o. It will start to use GDB on that program. Then you can set a breakpoint, type in break, followed by the line number of that program, or just a function name, right? For example, we have the function called fib recursion from our code example, right? So we can do the same thing, type in break fib recursion, right when it enters the function fifth recursion, it will stop. You can then run the program normally. Basically, it would just keep running. Or after you hit the breakpoint, you can continue by type in continue. You can go line by line by typing in step. You can print out the value of the variables by typing print. Print I will print the value of I, right? And that's a GDB cheat sheet. Many places. You Google GDB cheat sheet, there's tons of them out there. It depends on the preference of you want a bigger cheat sheet or smaller cheat sheet. The bigger ones will contain more commands. The smaller one would contain fewer, but the important ones that you're gonna come across, right? And here's the reference. There's a manual for C and the C standard library. This is the same as last time. So what we cover today will be included in the manual as well. And these are awesome places where you can use it as a reference. Sample code time. So I'm gonna do some example. First of all, right? We used Fibonacci before. So let's actually use an array. Now that we cover array. So we can modify our code and use array for our Fibonacci function. So let's do this. In the meantime, if you have questions, do let me know. This is the last slide today. The rest will be me typing. And then next week, we will do in-class exercise for practice. Basically, practice using basic C. I will need to boot up PuTTY. So let me change the setting. Okay. Oops. Go there, not this screen. Okay. Okay, I'm just going to copy the old lecture 5 sample code so that we can just start from the Fibonacci code, right? So it will be lecture 6 sample code section 1. All right, so we have fib.c, right? Over here, our loop implementation doesn't use an array, which is kind of annoying, right? So what we can do here is if fib of 0, we return 0, fib of 1, return 1, fib of 2, return 1. That's fine, right? And then we can create an array. So let me create an array ahead of time. Instead of results here, I will make result an array. And I will support up to 1000 number, 1000 Fibonacci value, right? So what I can do here is if it's greater than 2, what I would do is results of 0, so fib of 0 equal 0. Results of 1 equals 1 for I less than 0, right? I already done the first two, right? So if is actually I've already did the third one too. So result of 2 is 1. So fib of 2 is also 1, right? If I is 3 or more, if my input is 3 or more, I is less than or equal to input. I will just keep incrementing, right? And I'm gonna clean up this code a little bit because I don't need newer order anymore, right? I don't need order and newer. Why? It's already in my array, right? So I can say result of I, right now the first iteration input is 3. I want the third Fibonacci, fib of 3 equal result of I minus 1, right? Plus result of I minus 2. Let's test this out. GCC fib.c dash o fib.o. Oh, line 47 has something wrong. So let me check it out. Line 47. Oh, return results. Because we want to get the Fibonacci of n. So you should return result of input. Result is now an array. So fib of 42, now n is 42. Fib of 42 is that number. Simpler, right? Note that this will be a little bit slower. Any questions so far before I use pointer? Because you notice here, right? With result 1000, what if I want to get fib of more than 1000, right? What if I want to get fib of more than 1000? So let's do this. Let's say I want to get fib of 1001. It will say, I cannot do that because you are trying to access result of 1 over 1001, which I have not allocated. The OS protect you from it. Which is a bummer because let's say I want to know what's fib of 1001. What do? I can use a pointer, right? I can use a pointer. So instead of this, I would just say I want to create a pointer called results. And then I say, hey, initially I'll assign 1000 entries to it. Why not, right? Okay, and actually let's start with the what is the size you should start at? Give me a number. Give me a number of size. The initial number for size. A little bit too much. Can you make it like small so we can see that I grow the array? Sorry. No, smaller. Just do 9. Right. You said 9,000. So let me just do just 9. 9, right? 9. Okay. Initially, I have the size of 9. Now that I have results as a pointer, I can use this. This is valid. This is actually valid. It's fine. Result 0 means result 0. This is the same. Wait, this is the same as star results plus 0. This is the same as star results plus 1, right? This is the same. Okay, sorry. Wait, call me. So someone call me. So let me answer that phone real quick. I'll be right back. Oh my God. Curry just called me and asked where I am. And I'm like, I can repeat my address. Okay, so this is result 2 is the same as results, right? This is the same as results plus 2. So down here, whatever I do here is essentially it's the same as what if I say results star, like results plus I equal star, right? Results plus I minus 1 plus star results, right? Plus I minus 2. Exactly the same thing. The problem here we're running into right now is what? We have the size of 9, right? And let's say we want to calculate for 42. At some point, we'll run out of memory because we didn't allocate that much. So the first thing we can do here is to check if I, right? If I is greater or equal to size, right? Why do I check greater or equal to? I of 0 is result of 0. I of 1 is result of 1. We allocate for 9 item size is 9. It means that when I is 9, it's too much. When I is 9 is too many elements. We need to double the size. So this is when we need to double the size. This is the subroutine to double book. Right, double the size of my array. So what do we do? I again need a temp, right? A temp pointer. So I just did it up here. I create a temp that doesn't point to anything right now, which is fine, right? What I do here is temp equal malloc size of int, right? Multiply by size because I want to at least make 9. How should I grow? Let's say I grow by double the size, right? Plus 2, multiply by 2. This means that I'm going to create a space for temp with the size multiplied by 2. I just grow my array by double the size. The problem here, well, I need to copy things over. So I need another temp. Let me call it j. For j equals 0, j is less than size, j is plus plus. I need to copy everything from results. Start temp, right? Plus I equal results plus I. This is basically copy all the content of result over to temp. What's next? I need to free results. And then I will just make sure result now point to the same location as temp. That's it. Create the double the size, copy everything over, free the old one that you're not using anymore. Make sure now the old pointer point to the new location. And you can use result. Yes?
Why is it J?
Thank you. Yes, thank you. You just point a bunch. It should be J. Thank you so much. Yep. Everything here should be J, not I. Okay, so let's compile this. And ton of warning, implicit declaration of function malloc. Oh, I forgot to include standard library. So malloc is in standard library. So I need to go here and include them. Standard library on top of standard IO. Here, everything looks fine. Clip.o. Something failed. Okay, something failed. So let's actually try to figure out what failed. as I said, we can use GDB by called -g, right? Then I can use GDB fib.o. All right. First thing first, you can just call run. It will run everything until it actually crash, right? And I can type in backtrace, not backtrack, backtrace. It actually will show the line of when it crashed, right? So this is at line 51. At line 51, that's when you are running the loop. It gives you exactly that. Sometimes I'm trying to call a malloc and it crashed, right? So let's actually quit for now because it's too far. It already crashed, so I want to rerun. Break at fifth loop, right? And then run. Right now, size is 9. I can say step. Next line, result malloc equals size of int. I step again. There's no such file or directory for malloc. What the heck? Continue. Okay. Seems like malloc failed somehow, so I need to figure it out. What's wrong with the system? I'll come back once I fix it. Sorry, guys. This is weird. Somehow glibc cannot find malloc. Huh. Let me double check that if you don't mind on what's wrong with this. It should not happen, at least for the first malloc that I call. And since it's already 152, I kind of need to switch to another section anyway. So any last minute question before we come back to this, I just show you how to use GDB and I just found something is weird. So with the GDB, I now something is wrong with malloc. Oh yeah, sure. So yeah, you can ask it now because I don't think we have time to switch over to Discord. While you're typing, I'm gonna switch over to my desktop so I can join the WebEx. I can start the WebEx session for the other section while I'm answering the question, if that's okay. All right, so let me stop the recording as well because that's basically that's it for the class today. We'll continue on